In this video, we're going to talk about a really important concept in probability theory, and that's called independence. And knowing whether two events are independent or not, or more than two events are independent or not, really does change how we do calculations with those events and how we generally think of those events. So what does independence mean? Two random events are independent if knowing that one has occurred doesn't change the probability of the other occurring. A classic example of this is the weather. The probability that it will snow tomorrow changes depending on what the weather is today. If it's snowing today, what's the probability that it will snow tomorrow? That's quite high. If we are having a heat wave today, what's the probability that it'll snow tomorrow? That's quite low. So knowing today's weather changes the probability of tomorrow's weather. An example of two events that are independent, though, is rolling two dice together. If we roll two dice together, or even one after the other, the probability of getting a 1 on the first die is independent of the probability of getting a 1 on the second die. Just because one of the die cropped up as 1 doesn't change anything to do with the second die. So those two events are independent of each other. Note the language we use here. We use the words two events are independent of each other. We don't use the words two events are dependent on each other. Not very often. We do instead use the words not independent of one another. We can check if two things are independent of each other. So we can do that first check that we just thought about was, does knowing one change the probability of the other happening? But often we have a lot more subtle things going on. So we can check using this formula. If A and B are independent of each other, then the probability of the intersection of A and B is equal to the probability of A multiplied by the probability of B. So the probability that A and B happen at the same time is the probability of A multiplied by the probability of B. And if you think back to our tree diagrams, I said we can multiply along those branches. So probability of A multiplied by the probability of B given that A has already occurred. Well, now we're just saying it doesn't matter if A has already occurred. Probability of A multiplied by probability of B. So if this is true, then A and B are independent events. And sometimes it's quite subtle what events are independent and what are not. And we're going to look at some examples now. So the two examples we're going to look at both deal with a deck of 52 cards. So the first thing we're going to look at is the two events, drawing a heart and drawing a queen from a deck of 52 playing cards. And then we're going to look at what happens if we introduce two jokers into the pack. But first let's check, is drawing a heart and drawing a queen in a deck of 52 playing cards, are they independent events? So let's do that check. We want to check, is the probability of getting a heart multiplied by the probability of getting a queen equal to the probability of both those events happening at the same time? Well, they happen at the same time if we draw the Queen of Hearts. So what is the probability of drawing a heart? There are 13 hearts in 52 cards. What's the probability of drawing a queen? There are 4 queens in 52 cards. And what's the probability of drawing the Queen of Hearts? There's 1 Queen of Heart in 52 cards. Now this side does simplify to 1 over 52, and so that check is satisfied. Those two events, drawing a heart and drawing a queen, are independent of one another. Now what happens if we introduce two jokers? So we traditionally introduce a black joker and a red joker, one of each colour. So now when we introduce those two jokers, what is the probability of drawing a heart multiplied by probability of drawing a queen, and is that equal to the probability of drawing the Queen of Hearts now? Well, the probability of drawing a heart now, there are 13 hearts out of 54 cards this time. The 52 cards plus the 2 jokers. And the probability of drawing a queen, there are 4 queens out of 54 cards. And what is the probability of drawing the queen of hearts? There's only one of those out of 54 cards. Now, doing that multiplication, we get 13 out of 729 in its simplest form, and that is not equal to 1 over 54 in its simplest form. So actually these two events now are not independent of each other. What does that mean? That means that if I draw a card and I tell you this is a heart, you've got more of an idea whether it's a queen or not than before. Now, understanding when things are independent or not is vitally important to probability theory. I'm going to give you an example now, and this is a true life example where this misunderstanding of whether things were independent or not had some very severe consequences. So there was a court case in 1996. Sally Clark, she was a mother. Her first baby died suddenly of sudden infant death syndrome, SIDS. Then in 1998, her second baby died in the same way. This is a really tragic case. Now, the probability of a single cot death is 1 in 8,543. And the lawyers argued in court that for 2 of these to happen to the same mother, it would be so unlikely she should be imprisoned for murder. So look at the maths. The probability of a cot death is 1 in 8,543. So the lawyers argued that the probability of 2 cot deaths would be, as they are independent events of each other, probability of a cot death multiplied by probability of another cot death. 1 in 8,543 multiplied by 1 in 8,543. That is nearly 1 in 73 million. This is a tiny probability. And so it was argued the fact that these 2 could happen by chance is so small it couldn't be a coincidence, and therefore she was a murderer and she was imprisoned for murder. But this is not true. 2 cot deaths from the same mother are not independent events, and it has been shown medically that if you have 1 cot death, then the probability of a second cot death is a lot higher, and that's due to biology and circumstance and so on. So this was false, and eventually this trial was found to be wrong. Sally Clark was found innocent, but she didn't live a very nice or healthy life after that. It was a very, very tragic case. There's also something else going on here I want to discuss. So even if this was true, even if having 2 cot deaths on the same mother was independent events, it was argued then that the probability that Sally Clark is innocent is 1 in 73 million. How did they get to that? The probability of having 2 cot deaths was 1 in 73 million, not the probability that Sally Clark is innocent. They were assuming that the probability of innocence is equal to the probability of 2 cot deaths. So they were assuming that the opposite of innocence, murder, would be the opposite of having 2 cot deaths, so not having 2 cot deaths. So, and is this true? Is the probability that you're a murderer equal to the probability that you haven't had 2 cot deaths? Now, my mother is not a murderer, and my mother has not had 2 cot deaths, luckily. So this is also false reasoning. And this is a notorious problem, and is actually called the prosecutor's fallacy, where we mix up the probability of something like a murdering happening just being the probability of not being this one specific case of being innocent. This also brings me to another point, another misunderstanding in this trial. The probability that Sally Clark would have 2 cot deaths is 1 in 73 million. Now, the population of the UK is about nearly these days 70 million. So something we need to think about is being sort of humorously coined the law of truly large numbers. It's a very humorous reference to the law of large numbers that we looked at before. And what this says is that the more opportunities there are, the more random trials you do, the more likely you are of getting extreme results. So in Sally Clark's case, even if all those misconceptions were true and the probability that she was innocent was 1 in 73 million, well, she is 1 in 73 million, nearly. She's one of a lot of people in the UK, nearly 70 million people in the UK. So the more people in the UK there are, the more likely we are that one of these coincidences is going to happen. A nice quote about this by Penn Jillette, a magician, one of Penn and Teller there. He's the tall one that speaks. He said, 1,000,000 to 1 odds happen 8 times a day in New York City. What do you mean by that? Well, there are 8 million people living in New York City. So these extreme things, these absolutely crazy bonkers things that have tiny probabilities happen all the time because there's so many random trials going on around the world all the time. So the law of truly large numbers is not one of these formal mathematical laws, but it is true, and it is something we need to think about when we deal with probabilities, that the more random trials we do, the more likely we are to get extreme events.